on how it's made. Prams. Factory-built homes. Wood flutes. And bicycle tires. When it comes to choosing baby's vehicle, as with any set of wheels, there's no shortage of choices. Some parents prefer sporty models, while others opt for the elegance of a classic carriage. Either way, it's a stylish experience baby will likely sleep through. The classic perambulator, or pram for short. While this style of baby carriage is unmistakably British, this particular brand is Italian-made. Production begins with this machine, which bends steel tubing to form the pram's handle. The machine's every move is computer-guided for accuracy and consistency from pram to pram. Once formed, the handle is chrome-plated. They construct the base of the pram's frame out of a steel blade. An automatic feeder pulls the blade off the roll into a stamping machine. The machine's die cuts 54-centimeter long pieces with rounded ends. A press then bends each piece twice, forming it to the final shape. To assemble the base, workers align the pieces in the correct configuration with the help of a template. They add 2 steel rods for the front and rear wheel axles, then weld everything together. The base then goes off to be plated with chrome. When it returns, following some minor assembly steps, the full frame assembly begins. Workers mount 2 large oval steel springs on the base, securing them with pivoting hinges, which will allow the pram base to fold flat for easy transport. They hammer a rivet into each hinge. Then, using clamps, lock it in. The pram has a cargo basket made of chrome-plated welded steel mesh. It hooks onto the frame base. The pram's handle, meanwhile, has acquired a grip made of chrome-plated steel and genuine leather. They attach the handle to the frame with a plastic pivoting hinge, which enables the handle to fold down flat for transport. A spring-locking device secures the chrome-plated wheels to the axles. A foot lever at the rear of the frame activates the brake on both rear wheels. The pram body has an upholstered covering. They make it by layering a rugged polyester fabric over soft polyester batting, then fusing the 2 materials along the perimeter with heat generated by a high-frequency welding machine. This upholstered covering is made up of 3 sections. After trimming off the excess fabric, a seamstress stitches the 3 sections together. Then she lines the interior with cotton, a breathable fabric that's soft against baby's skin. The body structure is made of plywood sides, poplar bottom supports, and sturdy fiberboard ends. After cushioning the sides and edges with polyester batting, they dress the body with the upholstered covering and lay in a cotton mattress. After installing metal carry handles, they affix the pram's canopy, driving the screws through the upholstery into pre-drilled holes in the plywood structure. The canopy is made of water-resistant laminated polyester sewn over a frame of steel ribs. The ribs are hinged, enabling the canopy to be opened and locked or collapsed. The snap-on upholstered front cover, like the canopy, is made of laminated polyester to protect baby from rain and cold. Metal pins underneath the body fit into slots on the frame, locking in securely with a lever. For quality control, the factory regularly tests random samples, putting them through 100 hours of a simulated bumpy road at a speed of 5 kilometers an hour. The pram must survive this not very baby-friendly journey with nothing beyond normal wear and tear. Documents say a 2-story panelized frame dwelling was shipped from England to the US in 1764, but perhaps the first real predecessors of modular homes were sold from catalogs in the early 1900s. These kit homes eventually led to houses built in a factory setting. Not only do factory-built homes cost less, they tend to be much more energy efficient and versatile. They're quick to build and offer a variety of space options, with all the comforts and conveniences of conventional houses. They provide ease of living and ease of construction as well. In the factory, a worker welds the steel pieces that make up the undercarriage chassis. Its length depends on the demands of the customer. Workers move the completed chassis to the next part of the factory. They pull a layer of polyethylene over the length of the chassis and roll a blanket of fiberglass insulation on top. Framing for the home's subfloor is in place, along with water lines and heating ducts. An assembler nails the framing joists to a perimeter rail. They apply glue to the floor joists and cover the floor framing with composite wood floor decking. The assemblers nail the decking into place. A worker glues vinyl tiles onto the decking. Flooring comes in a variety of materials, including marble, ceramic tile, carpet, laminate, and wood. In another part of the factory, framers are working on the home's interior walls. Building them on tables tends to make them straighter and stronger than walls that are built standing upright. Workers fill these exterior walls with insulation. The efficiency of the insulation depends on the climate in which the home will be installed. Workers apply adhesive to the studs. They position interior paneling and staple it into place. This is the factory's cabinet shop. These specialized cabinet makers use a wide variety of materials and styles to create bathroom and kitchen cabinets, such as this double sink galley cabinet. Workers begin putting cabinets on the floor of the home. In factory-built homes, cabinets are installed before exterior and partition walls have been put in place, making the job a lot easier and more precise. Once the cabinets and interior walls are done, workers install exterior walls. They add this wall with the help of a crane. The wall fits precisely into place. Both the wall and interior frame are pre-caulked, and when they meet, they form an airtight seal. Workers move this section to the next station in the factory. Using a crane, they lower the sealing system into place. The sealing system is all one piece. Workers lower it carefully, making sure the ceiling lines up precisely with the walls below. All the walls are pre-caulked, and once they set the ceiling down, it's completely sealed, adding to the home's energy efficiency. Workers blow cellulose insulation into the attic cavity to form a thermal barrier. Before adding the exterior roof covering, specialized roofers put wood decking over the trusses and staple it into place. PVC piping is used to drain the home's wastewater and sewer lines. Assemblers now install lap siding over a moisture barrier. Sidings can be composite, vinyl, cement, or wood with different finishes. This cement board is impervious to bugs and won't rot. A drywall finisher is inside, taping and texturing the gypsum wallboard and applying plaster to walls and ceilings. This particular home is ready for off-grid use. Solar panels on the roof charge batteries by day. The batteries store power for use at night. This single-module cottage, like most factory-built homes, can be transported and delivered anywhere in the world. Comfortable, affordable, and energy-efficient, factory-built houses have redefined the dream home. The wood flute is one of the oldest musical instruments. Every culture had a version, but the Native American one has a particularly soulful sound and a very romantic past. For centuries, Native men played the flute to court their beloved, and it became known as the courting flute. Today, the courting flute courts a wider following. Its appeal reaches beyond the native community. With 2 chambers instead of 1 and a block whistle mechanism, the Native American flute is unique. It takes less skill and effort to play it, and the tranquil tones offer relief from the din of the modern world. To make one, a native craftsman cleanly splits a piece of cedar with a table saw. No need to craft it entirely by hand when there are now mechanized woodworking tools. With a router, he carves a hollow in one end. It will be half of the flute's slow air chamber, which is the first chamber to receive breath. He now shapes the much longer sound chamber. It's the one that sets the pitch of the notes. After routering corresponding hollows in the other cedar half, he applies glue and spreads it evenly. A consistent application is crucial. Any gaps, and the flute won't work. He matches up the pieces and clamps them for a solid seal. The clamps squeeze out some glue, so he wipes it away quickly before it dries. He cleans up the inside with sandpaper wrapped around the end of a spinning metal rod. Once the assembly dries, he builds the mouthpiece, using a band of dark African wood for contrast, and then a thick chunk of myrtle wood. Myrtle wood is finely grained and hard, so it will hold up to heavy use. He drills into the wood to carve out the mouthpiece and breaks through to the slow air chamber. It's time for a spin in the lathe. The craftsman turns a wheel to move a chain-driven router along the spinning wood. It shaves the wood a little with each pass to take it from square to round. He mills the flute between the two chambers to create the nest, a flat area with holes upon which the block will rest. It's through this area that air passes from one chamber to the other. He cuts off splinters that could ruin the sound of the flute. He builds up the nest area with a precisely shaped flat piece of wood. He bores through it into the nest hole to reopen it and give it its final shape. He carves a ramp to compress and speed up air as it passes from the first chamber to the second. He drills the smaller sound hole. After he files the sound hole to a rectangular shape, he positions the block over the nest. It's this wood block that creates the clear whistle tone of the flute. The length of the tube determines the pitch of the instrument. He blows into the flute and checks the dial of the digital tuner. The key is a bit too low, so he cuts the end to take it up to G on the scale. Satisfied with the pitch, he drills 6 finger holes. He spaces them in a precise configuration. The size of the holes varies slightly to help create the desired notes. He files the edges of the finger holes on an angle to bring the notes into tune. He tests the flute again. It's in the correct range, no tweaking needed. He now tapers the mouthpiece using a belt sander. He uses a fairly rough grit to transform the cylindrical mouthpiece into a cone shape that's easier on the lips. He scrutinizes the newly sculpted mouthpiece and confirms that the shape is right. He signs and numbers it with a wood-burning tool. Finally, he coats this Native American flute with protective acrylic. Using modern woodworking techniques, a centuries-old musical instrument has been updated, and it's now ready to entertain. In the first half of the 18th century, bike tires were made of wood, then metal, and after that, solid rubber. Finally, in 1888, a Scottish veterinarian named John Dunlop developed an air-filled rubber tire to give his son's tricycle a smoother ride. The air-filled bicycle tire continues to be the hottest thing on 2 wheels, but a modern spin on the concept takes it into the 21st century. Computer designed for minimal road resistance and aerodynamics, the inflatable bike tire has had a major update. Additives such as mineral oil, sulfur, and carbon black make the tire more elastic and durable. And they use a combination of natural, synthetic, and recycled rubber. They weigh and bag it and send it into an enormous hot mixer. The white blocks are the synthetic stuff. Other ingredients include anti-aging agents. During the mixing, a chemical reaction causes the plastic bags to disintegrate, leaving only the desired elements. The components melt into a rubbery dough, and rollers squeeze it into thick sheets. This rubber sheet will now be used to make the tire, beginning with the tread. Narrower strips enter an extruder. It heats the rubber to soften it and takes it through a die to form a strategic profile for the bike tire tread, leaving it thicker in the center and thinner along the edges. The tire tread rubber now takes a long, cool dip in a tub of water. This solidifies it, setting the profile shape. An automated spool winds it up, with a fabric separator between the rubber layers to keep them from sticking together. In the meantime, rubber for the bike tire casing has been reinforced with nylon mesh. This casing rubber now enters a cutting station. Blades slice the casing rubber into strips that are the correct width for building bicycle tires. It will take several to build one tire. An employee pieces all the strips together for production. He winds the assembled strips of casing rubber onto fabric backing. Neatly rolled onto spools, the rubber can be stored until the tire assembly. And they're ready to roll. An employee winds the nylon reinforced rubber around a metal drum. She then applies 2 strong Kevlar threads for the tire beads. The beads will hold the tire to the wheel rim. Once in place, devices fold the rubber at the sides over the beads. She then wraps a Kevlar strip around the tire casing. This is for puncture protection. A machine now rolls the tread rubber onto the Kevlar strip. With all the layers of the bike tire in place, she removes it from the drum. Then it's over to the branding station. This worker arranges labels on the tire rubber and bonds them to it with hot metal plates. The next employee places the tire rubber in a clamshell-like mold. This mold contains a large balloon or bladder. They pump steam into the balloon, causing it to press the rubber against the sides of the mold. This shapes the tire, including the tread, and fuses all the layers together. It also transforms the tire from limp to rigid in a process known as vulcanization. And it's quite a transformation. This is the tire before vulcanization, and this is the tire after. One tire from the batch undergoes a gamut of tests. This one simulates road wear. The tire spins against a metal wheel until it goes bald, usually after several thousand kilometers of spinning. This confirms that the tires from this production run are long-wearing and can go the distance. They also test for puncture resistance and pressurization. If the bicycle tire passes all the tests, this batch is ready to test human endurance.